All right, folks, let's get started here. I posted this morning all of the resources for midterm 3. The department posted their practice exam, so I'll just show you where those are. As you know, I like to be very predictable. So it's just like before. I have a page here, resources for midterm 3, all the information you need, like what to bring, all those things. The first link here, preparation for exam 3, this link brings you to the page that the department posts with the 3 Carmen style practice exams. Note that, the grades, if you take these exams via Carmen, it does not affect your overall grade. They're in the grade book, but they're weighted as a 0%. So it does not affect your overall grade. It just allows us to do a little statistics from our ends of things. But you can use the PDF versions as well to look at those questions. But if you do want the video feedback, you actually do have to take the exam, but you can just open it and then submit it. And you'll get a 0, but who cares? But you can get the video feedback and the answers once you submit it. So there's the department exams, and then I have my paper exams here, though this time around the department beat me in posting these things. So I only have 1 paper exam posted and the key, but I'll get another one sometime this week on here. And so these paper exams, they're worded a little bit differently just because I write them. So do keep that in mind, but it's just more practice problems for you. And, my keys are very colorful and very descriptive, so that can be helpful. So here are all the resources for you to study for midterm 3. So hopefully, I hope in recitation, when I ask you these essay questions of what advice would you give yourself earlier on in the semester, take that advice to heart, because really the chemistry department and me, we don't bestow grades on you. You earn the grades that go towards the grade book. It's all in your hands. And a situation happened this morning that I think really reflects my teaching philosophy. So this morning, I had to go to the chicken coop to do some chicken stuff. And when I opened the gate, a chicken ran out. All right, and it sucks because I can't get home until dark, so I didn't want that chicken to stay out all night. So this morning I spent an hour running around trying to catch it with a net. All right, so I was running after it with a net, and I fell multiple times because it was slippery out. So I spent an hour doing that, and I didn't catch it. It just kept running away. So I went back inside and calmed down, try to think my way through this to try to catch it so it doesn't die out in the wild. So a couple hours later, instead, I went to the coop. Their run, I isolated the other chick so I could keep the door open to the run and just let the chicken, wander in on itself. And I think that really reflects on my teaching in that, not that I'm comparing you to chickens, but that I like to make and design an environment where you basically take into your own hands your own learning, and that I can lead you to the right answers, lead you to the correct kinds of motivations and study habits. But in the end, I can't take a net and catch you. All right, that's not very fun for either of us if I'm the one chasing after you to tell you to study. So in this case, it's really up to it's in your own hands, and you gotta lead your way back to the coop, all right, to safety. And so that kind of got me thinking. I don't know if it relates, but this morning was traumatizing for me. So I just wanted to share that. All right. Okay, so where do we leave off? Any questions about the midterm? All right, it's gonna cover chapters 7 through 9. We might finish chapter 9 on Wednesday because we don't have class on Friday, but if not, we'll definitely finish it on Monday. So there we go. All right, so we left off talking about valence bond theory. So we are expanding on our idea of the electron that the electrons, when we draw them in Lewis structures, they are not dots on a page, that they actually exist in space. So that's why we, considered Vesper theory to think, okay, how we draw these Lewis structures aren't really, right. We have to think about electron repulsion, the bonds and the lone pairs, how they orient themselves in space, and the names that we call them. So valence bond theory expands on that and thinks about, okay, yes, electrons are not dots on a page, they exist in orbitals. So bonds are formed when electrons on adjacent atoms overlap their orbitals. So the more orbital overlap, the stronger the bond. You can think of, like, here's this s orbital here, two different s orbitals, whoops, and as we, come on. All right, so we have two separate s orbitals on two different hydrogen atoms, but as we bring them closer together, all right, so we have electron density in both of those circles here. As they overlap, it's this space in between, this shared space where the electrons will reside, forming that covalent bond. And so we looked at some examples here. We're just kind of rethinking of, okay, before we said unpaired electrons is what made covalent bonds. Now let's think about, where are those unpaired electrons originating from? In diatomic hydrogen, they're originating from one s orbital. So we can think of the overlap of two s orbitals. There's that head-on overlap that creates our covalent bond. We can expand this example to something like HCl. And again, you just consider what orbital is that unpaired electron. In hydrogen, it's still a 1s orbital, so that's why it's a circle. But on a chlorine atom, this unpaired electron, if we were doing Lewis structures, that's the one we're pointing at. We're just thinking, okay, what orbital is that in? Drawing the electron diagram helps us. We see that it's in a 3p orbital. And then lastly here, diatomic chlorine, those two unpaired electrons form the bond. Both of them are now originating from p orbitals, and we get the right type of head-on overlap here to produce these shapes. Two atoms will always make a linear, molecule. All of these interactions are linear. So now let's expand to our more sophisticated shapes, all right? So all of these are linear. S and p orbitals, atomic orbitals, when they combine, can make these linear shapes. The problem is, we talked about other shapes in Vesper theory, trigonal planar, tetrahedral. I don't know about you, but there are no atomic orbitals that have the shape of a tetrahedron. That's like a new shape that we've encountered. And so we need a new theory to help us explain this shape. And that's the theory of hybridization, where sometimes we need to combine atomic orbitals to produce these new shapes. So mathematically, so I'm going to just show you like the easy way to kind of think about this, but there are some mathematical and like symmetry related linear algebra that you need to do in order to calculate these new shapes, but we're just going to think about what atomic orbitals do we need to combine to get the certain shapes that we need. So thinking about, we talk about molecules that are linear, trigonal planar, and tetrahedral. So basically the big idea here is, depending on the number of electron domains of your central atom, that number that you calculate from the beginning of this chapter, that number tells you the number of atomic orbitals you need to combine to produce that new shape. So for example, a linear molecule, all right, if we had a linear molecule X like that, okay? How many electron domains are around X? Two, right? Just two bonds, that's it, all right? So I didn't draw any lone pair, so it's just two bonds right there. So if there are two electron domains, how many atomic orbitals do I need to combine for the hybridization of that central atom? Two, right? Two electron domains, two atomic orbitals. So specifically those two atomic orbitals that we need to combine is an s orbital and a p orbital. And so if we combine two atomic orbitals, we get two hybrid orbitals out that are in that correct shape of linear. All right? Okay, let's just keep going, and hopefully the repetitiveness and the trend, hopefully it'll sink in. All right, so let's pretend we have something that's trigonal planar. All right, so how many electron domains are there? 3. So how many atomic orbitals do we need to combine? 3. All right, so the atomic orbitals that we combine are an s orbital, a p orbital, and a p orbital. Right, those are 3 atomic orbitals. So how many hybrid orbitals do we get out? 3. We also get 3 hybrid orbitals, so here they are. And so the great thing about these hybrid orbitals is that they are in the correct orientation. When you do the matrix math, all right, of combining these 3, or doing a linear combination of these 3 atomic orbitals, you will get 3 hybrid orbitals that are all 120 degrees from one another, describing our trigonal planar shape. So that's how hybridization gets us the shapes that we want. So let's keep going. What about something that is tetrahedron, like a carbon atom? How many electron domains are there? 4. So how many atomic orbitals do we combine? 4. So here they are. We combine an s orbital, a p orbital, another p orbital, and another p orbital. So the 3 p orbitals are in the x, y, z planes, or whatever is listed there. All right, so all the different orientations of those p orbitals. So when you do a linear combination, although you don't actually have to do it, but if you do one, you combine 4 atomic orbitals, or s, p, another p, and another p. You get 4 hybrid orbitals out that are consistent with the tetrahedral shape that we predict with 4 electron domains. So they're all 109.5 degrees apart. So that's the great thing about hybridization, is that yes, it complicates, it's a little bit more complicated than our previous theories, but it's also consistent with our other theories like Vesper theory that we just talked about. So this is what allows us to get our new shapes. So let me just show you an example. So just know, basically what I've boxed here is the important part and what allows you to answer a lot of questions on the homework assignments. All right, okay, but here's the strategy, just so you have it somewhere. Typically a question will ask something like, okay, here's a molecule like PF4+. Okay, the molecule or the ion PF4+. What is the hybridization of that central phosphorus atom? That is what a typical homework or exam question would be like. So the strategy here is, once you have the molecule, you're given a molecule, the first thing you want to do is draw the Lewis structure. So what is that? Our 6 steps? I told you that, everything we learned in chapter 8, it builds. So the first thing here is to draw the Lewis structure. So since we're trying to determine hybridization, that's related to valence bond theory, the next thing we want to do is, apply Vesper theory and look at the electron domains around the central phosphorus atom in our example. So I think PF4 looks something like that. It's 4 electron domains. And so once you have the Lewis structure, you count the number of electron domains, then you use our whole equation up here that tells us how many atomic orbitals that we need to combine, and then that will tell you the number of hybrid orbitals you get out that will describe the bonding. So I'll show you the kind of the magic that happens here that helps us kind of bring together the aspects of valence bond theory, where orbitals actually have to overlap in space to form covalent bonds. This is why we need to form hybrid orbitals. All right, so here's an example. All right, so let's look at beryllium dichloride. So here's the Lewis structure, so I already have it right there, all right? So how many electron domains are around the central beryllium? 2. So what orbitals do we need to combine to hybridize that central beryllium atom? S and P, because we want to combine 2 atomic orbitals. So I'm going to show you the details here of why this matters. So 2 electron domains, all right? So we're going to combine an S and a P orbital. So sometimes we call it sp hybridized, that central atom. And so I'll show you what that means. So this is kind of our answer here for valence bond theory, but I want to show you the details, because it will make more sense here in a little bit. Because the idea here is, when we think about a beryllium atom, all right, when we think about a beryllium atom, I wrote up here, what is the electron configuration of beryllium, like off the periodic table? 2s, how many electrons there? 2, and those are its valence electrons. Those are the electrons involved in bonding. So I have the picture here. Are there any unpaired electrons on a beryllium atom? No, there aren't. So, but in this picture, beryllium forms 2 bonds. So where the heck are the unpaired electrons coming from? Because it looks like in this picture, everything is paired. This is why we need to hybridize. On a beryllium atom, there are no unpaired electrons, but we know beryllium will make covalent bonds. So we need to basically force the atom to make unpaired electrons to form bonds. So we said that beryllium has 2 electron domains. So we need to hybridize 2 atomic orbitals to produce 2 hybrid orbitals. So this is what the picture looks like. On the left here, I have the beryllium atom, where I have basically the electron configuration drawn out. We have a 2s subshell and a 2p subshell with the 2 electrons in the 2s. But the problem is that there are no unpaired electrons to form those beryllium-chlorine bonds. So what we're going to do is, we already said, we're going to combine 2 atomic orbitals to produce 2 hybrid orbitals. So that's what these 2 red these big parentheses are. All right, this is, I'm trying to tell you, hey, I'm going to hybridize these 2 atomic orbitals and produce 2 new hybrid sets on the other side. So basically, we combined an s and a p orbital, and we spit out 2 different sp hybrid orbitals out on the other side. So you see that total, there's a total of 4 orbitals on, before we hybridize, 4 orbitals on after we hybridize. What we just did is we just changed basically the energy of this, this hybridized set. All right, so now that we have these 2 hybrid orbitals, I'll mention to you here that when you make hybrid orbitals, they are degenerate. Do we know what that word means? Same energy, yeah. So like, for example, the 3 different p orbitals, like when I draw the 3 boxes, those are degenerate. So when we fill electrons, we fill them singly. All right, so we apply Hund's rule to degenerate orbitals, that you fill them singly before you start filling them up again, or doubling up on them again. So these hybrid orbitals here are also degenerate. So do you see, instead of putting the 2 electrons in one box, we spread them out because those 2 hybrid sets are degenerate. So do you see what hybridization does now? Now that we've rearranged our electrons in these new orbitals that are in the correct orientation for VSEPR theory, now these 2 unpaired electrons can go on and form covalent bonds with those 2 chlorine atoms. Because if you look at the picture here, can these paired electrons make covalent bonds? No, it can't. But these ones can once we hybridize. So that's kind of the beauty here. All right, so so some details about these hybrid orbitals. Each of these orbitals are a particular, it's a different orbital that can house different electrons here. So that's what these 2 pictures represent. We have one lobe that's pointing like on the x-axis, and the other one has a really large lobe on the negative side of the x-axis. So we see that those 2 orbitals are 180 degrees away from each other. That is linear. That describes 2 electron domains. So this is what I want you to understand, is that when we draw these 2 boxes, it's 2 different orbitals. But sometimes books are lazy, and sometimes they'll draw them like this. Well, they'll draw them all on top of one another so you can clearly see the shape. But what I want you to understand is that when we talk about hybrid orbitals, each of these big lobes is an orbital that can house 2 different electrons. So when you draw it this way, you're essentially combining orbitals. So this picture is showing 2 orbitals at the same time, neglecting the tiny lobe on the other side. They just do this because it helps us see the shape more, but it's actually not correct, just so you know. But it does help us see the shape. All right. So there's beryllium. And now that here's our new hybridized set, this next slide shows you how the bonds can be set up to make our molecule. So here's our new hybridized beryllium that has now unpaired electrons that can form bonds. And so if we add those chlorine atoms there, and again, this is valence bond theory, so we're thinking, okay, where are those unpaired electrons that are overlapping in space to form our covalent bond? So for the central beryllium atom here are the 2 electrons forming one covalent bond, a p orbital on chlorine. So that's what this picture is showing. Here's our electron and a p orbital on chlorine, overlapped with an sp hybrid orbital on beryllium. So that's what this lobe is showing on the other side. So although these 2 purple lobes, each of these is a different a different orbital, just so you know. All right, and then on the other side, the other unpaired of beryllium is going to overlap in space with the other unpaired electron on chlorine. And it happens to be in a p orbital, so that's what we have drawn down here, and we see it's the perfect overlap we need to form that covalent bond. So basically, hybridization allows us to make unpaired electrons, all right, so we can form these covalent bonds according to valence bond theory. And the great thing is that it's consistent with Vesper theory, the shapes that we studied in the beginning of this chapter. Okay, so there we go. Let's do another one. Because people look confused. We're not going super deep into it. I kind of just want to give you the gist of it, but believe me that it's useful. It is useful. So let's look at an example with 4 electron domains, and hopefully you see the issue if we just treat that central carbon atom using its neutral electron configuration. So when we think about that a carbon atom, let's draw out its electron configuration. So for carbon, it's helium, 2s2, 2p2. So if you draw out those electrons over here on the left, okay, if you just look at these electrons, how many, according to the electrons, how they're drawn, how many bonds can carbon make? 2. But that's a problem, right? Because carbon has how many bonds in this Lewis structure? 4. How does it do it? It has to hybridize. All right. So let's go through the process. Carbon has 4 bonds, 0 lone pairs. So how many electron domains? 4. So how many atomic orbitals do we need to combine to hybridize? 4. How many hybrid orbitals do we get out? 4. So that's what we're going to do. We're going to draw the normal, from the periodic table electron configuration. We're going to combine 4 of those atomic orbitals. So if we combine those 4 atomic orbitals, we get 4 hybrid orbitals out. The special thing here is that the hybrid orbitals are degenerate. And that's why in this picture, I've drawn them all together. See, they're all together. They're all the same energy. So now what I'm going to do is redraw those 4 valence electrons on carbon, but this time following Hund's rule with the new energy of the hybrids. So now do you see the 4 electrons, because we're following Hund's rule, get spread out all singly? And then now we have 4 available unpaired electrons to form the covalent bonds that we need. In this case, in this example, it's with the unpaired electron in chlorine. All right, so this is how we get the four bonds that's being dictated by valence bond theory. All right, do we see that? So I just said that central carbon atom is sp3 hybridized. So the bond that is being formed, all right, right here, this bond is being formed between the overlap of a carbon's sp3 hybrid orbital. Where is the electron on the chlorine atom? What orbital is overlapping with that hybrid orbital? It's from its p orbital, so it's the exact, same exact thing we've been talking about in the other examples. It's with its p orbital, because that's where the unpaired electron is on that chlorine atom. So the trick is that most, when we hybridize things, it's the central atom. It's the outer atoms typically do not need to hybridize to follow our valence bond theory. It's only the central atom. All right, so let's look at it in another example. Let's look at ammonia. So how many electron domains are on the nitrogen in ammonia? 4. So how many atomic orbitals do we combine? 4. Which ones are they? S, P, another P, and another P. So if we combine 4 atomic orbitals, how many hybrid orbitals do we get out? 4. Okay, so let's draw it. So actually, the hybridization deal will look exactly the same as our carbon example, right? So we combined 4 atomic orbitals to get 4 hybrid orbitals. The difference is the number of valence electrons. Carbon has 4 valence electrons. How many valence electrons are on nitrogen? 5. But no problem, we still follow Hund's rule and we put in those electrons. So we put the 5, Hund's rule, following Hund's rule, put the 5 electrons in. So once we put the 4 in, that 5th one will be spin paired with one of them. So I hope you see the subtlety here the magic that's kind of happening here. Remember, it's these unpaired electrons. Those are the ones that form bonds. So according to this hybridization, how many bonds will that nitrogen make? 3. Then what the heck is this? That's the lone pair on nitrogen. All right, so each of those unpaired electrons are going to overlap with the lone pair on hydrogen. And then that one right there, that is our lone pair on nitrogen. Is that consistent with the Lewis structure that we drew? Is the hybridization consistent with the shape that Vesper theory thinks about? Yes, and so that's kind of the power of this theory. I love valence bond theory. I think it explains a lot of the phenomena and the idea of bonding, right? Sharing unpaired electrons. It explains a lot, all right? So there we go. So I hope you see it. You see it? Okay, so let's, are we gonna do another one? All right, let's do water. Water, okay. So, but I'm not going to give it to you, all right? So remember the steps for valence bond theory. If you're given a molecule, usually the question asks something like, what's the hybridization of the central atom or something like that. So if you're given water, the first thing to do is to draw the Lewis structure. I hope by now you know what water looks like. We have oxygen, 2 hydrogens, and then how many lone pairs? 2, yes, 2 lone pairs. There we go. But if you follow the 6 steps, you'll get this as well. Okay, so how many electron domains? 4. Just for fun, what is the shape as well? What is the electron domain geometry? Tetrahedral. But then what is the molecular geometry? Bent, yes. Bent with what bond angle? 120, closer to 120 degrees or 109 degrees? Closer to 109, slightly less than 109. And because the idea here is that our electron geometry is our template, all right? So there are all of our electron domains, but we already said 2 of them are lone pairs, so we just cover those lone pairs up, and say, okay, the actual bonds make a bent shape around 109 degrees. All right, there we go. And finally, the last thing we can kind of ask about this molecule is what is the valence bond description or the hybridization of that central atom. So we take that electron geometry number, 4 electron domains. How many atomic orbitals do we combine? 4. How many hybrid orbitals do we get out? 4. What's the hybridization if we combine 4 atomic orbitals? sp3, and of course you can kind of look at the name sp3, p3 meaning p squared. So there's an s and 3 p's, so that's 4 atomic orbitals, 4 electron domains. All right, so there are my 4 boxes. I'm just going to draw the hybridized orbitals now, but the idea here is how many valence electrons do we put in those new degenerate hybrid orbitals? 6. Did you just guess that? No. The 6 electrons come from the oxygen atom that we are focused on right now, right? Oxygen has 6 valence electrons. So we place those 6 electrons following Hund's rule. So 1, 2, 3, 4, 5, 6. So do you see the 2 unpaired electrons we need to form the bonds with the 1s electron on those hydrogen atoms that they're attached to? And then what are these guys on the end here? What are those guys doing? Those are the lone pairs. Beautiful. Don't you think that's beautiful? You know, sophisticated people, they look at artwork and they get like, you know, chills, they get goosebumps. But me, when I look at this valence bond theory and I see, oh my gosh, those are the unpaired electrons that I need for bonding, the covalent bonds, they're the lone pairs that are consistent with Lewis structures. That makes my, like, gives me goosebumps. Okay. All right, so here's everything, all right? Basically, with valence bond theory, what will get you through this is that the number of electron domains around your central atom is the number of atomic orbitals you need to mix. So the order you do it in is S, P, P, then P. And then that's the number of hybrid orbitals you get out, and the note here is it's degenerate. So just imagine, I guess if we went with trends, what if we had to do 5 electron domains? Can we add another p orbital? No. So typically the thought is you can add d orbitals, all right, d orbitals to get 5 and 6 electron domains. Christmas music already? All right. And so this is why when we think of 5, 6 electron domains, those examples are only for what we call hypervalent molecules. So do you remember the rule? Do you remember the rule about central atoms exceeding their octet? What was the rule? It had to be above or lower than period 3, n equals 3. What's special about n equals 3? That's when you have access to d orbitals. And so that's basically why, because if we think about something with 5 electron domains, it has to be sp3d hybridized. You need to have access to that d orbital. But the thing is I think that works beautifully with our description of valence bond theory, but calculations say that that's actually not true, but it still works with our theory. So if you read the textbook, they have a little blurb on hypervalency, but just know if you need to get to 5, 6 electron domains, you need to start adding d orbitals, but it works perfectly, and I'll show you an example here. But basically, this is just an overview of all the different shapes. These shapes should look familiar. The only difference now is we've added this idea of hybridization. And note that these shapes are consistent with the bond angles. The angles of the hybrid orbitals are consistent with the shapes we learned in Vesper theory. And yeah, 5 and 6 electron domains is controversial. But if you say that, you know, something that's octahedral is sp3d2, like no one's going to blink at you except for really, really smart computational chemists, probably. All right, so let's do some examples here, all right? So these ones are hypervalent, so let's just try to use our skills here, all right, the steps, to approach valence bond theory. So I have the Lewis structures for you, so it's super easy. All right, so this phosphorus atom, how many electron domains are around it? 5. For fun, let's pretend like we're doing the Lewis structure. What is that shape? Trigonal bipyramid. Yes, or TBT. Wait, trigonal bipyramid. Yes. All right, because it's 5 electron domains where it's 5 bonds, 0 lone pairs. So every single electron domain is a bond. So there's no lone pairs to worry about. So if you think about it in terms of like bond angles, there's 120 degrees and 90 degrees thrown in there. So based upon our electron domain geometry number, what does the hybridization of that central phosphorus atom need to be? sp3, that's 4 electron domains. So to get the 5th one, we just add a d. All right, so based upon the hybridization, if we drew out the orbitals, how many boxes would be in our hybridization? How many boxes? If there's 5 electron domains, if we combined 5 atomic orbitals, we get how many hybrid orbitals out? 5, so we would draw 5 boxes, right? 5 boxes. So how many valence electrons are on phosphorus? 5. 1, 2, 3, 4, 5. There are 5 unpaired electrons to go on and make 5 covalent bonds with fluorine atoms. There it is. So that's what I mean, that even though 5 and 6 electron domains is controversial, it still fits with our description of valence bond theory, that we need to, you know, move around these electrons to make them unpaired to form bonds. Because let's think about it. Remember our Lewis dot symbol for phosphorus? Do you remember what it looked like? It looks something like this: 1, 2, 3, 4, 5, like that. All right. So according to this picture, phosphorus can only make how many unpaired electrons? Or sorry, make how many bonds? 3. But we know phosphorus can expand its octet, so we need hybridization to explain that. This is how we get our 5 unpaired. All right, next, let's do bromine trichloride. So how many electron domains? 5. So what's the hybridization? 5. Yeah, sp3d also. Okay. For fun, let's draw it. So how many boxes should I draw for my hybridization? Yes, 5 hybrid orbitals because I combined 4 atomic orbitals. So let's see what this would look like. So bromine has how many valence electrons? 7. So let's put the 7 The 7 electrons in those 5 degenerate hybrid orbitals. But the special thing is that we need to do Hund's rule before we start pairing up. So if we do that, 1, 2, 3, 4, 5, I need to place 7, so 6, 7. Do you see those hybrid orbitals that we've drawn while we've replaced those 7 valence electrons? There's 3 places, 3 unpaired electrons to go on and make covalent bonds with chlorine. And then what are the last 2 things there? The lone pairs. And is that consistent with our Lewis structure? Yes, it is. All right, so again, I think it's as beautiful as the Mona Lisa. All right, okay, and the last one here. Based upon the Lewis structure, how many electron domains? 6, so what's its hybridization? sp3d2, yes. All right, and then you can do the same thing. 6 boxes, okay? You put the 7 electrons in there, and you'll see that you take into account that one unpaired or that one lone pair that's there. Yeah. What's the shape? Okay, yeah, we can go through these because I skipped them. So the shape of the first bromine compound, so if it's 5 electron domains, its electron geometry would be trigonal bipyramid. All right, that's the shape the electrons make, all right? That there's 5 domains of electrons. But the problem is that there's 2 lone pairs that we need to take into account of. So where do those lone pairs preferentially go? The belt region, the equatorial position. So in that case, you cover up 2 of the legs, 2 of the bonds on that belt region in trigonal bipyramid, and you see what's left is a T shape. Yeah, and that's what the Lewis structure is trying to. Here, I try to draw the Lewis structure to match, the shape, but the Lewis structure technically doesn't have to. It just needs to follow the octet rules and stuff, the rules that we talked about before. So same thing with BRF5. 6 electron domains would give us a electron geometry of octahedral. So that's the template we start with. All right, so octahedral, where we have 6 electron domains, but only one of them is a lone pair. So just make they're all equivalent, so just make one of them a lone pair, and if you cover that up, what is left? Square pyramid. All right, so basically you just literally erase this and you think, oh, what shape is that? Square planar, yeah, okay. There we go. All right, so that's hybridization. Okay, not too bad, right? Not too bad. You don't have to do any linear combinations, so it's not that bad. And it explains a lot. It tells us how we're getting unpaired electrons to participate in bonding. All right, so let's put it together. Identify the hybridization for these atoms. So what's the strategy? We want to count electron domains around our central atom, and then you just choose the right atomic orbitals to combine. So let's just go left to right. This carbon atom on the left has how many electron domains? 4. So the hybridization is sp3 because it's 4 electron domains, so combine 4 atomic orbitals. So our hybridization is sp3 hybridized. And so, of course, this sp3 hybridized orbital, or the hybridization here would have 4 different boxes within its hybridization. All right, what about this carbon atom? Is sp2, because there's only 3 electron domains. So 1, 2, 3. All right, remember that double bond only counts as 1. All right, so because that carbon atom down here only has 3 electron domains, it's sp2. Let's do a little bit of Vesper theory review. What is the predicted shape of that around that carbon atom? Trigonal planar, yeah, because it's 3 electron domains, right? So all of those are still true now. Okay, what about this oxygen atom on the end? sp3, and the idea here is that it still has 4 electron domains. Those lone pairs count. All right, those lone pairs count in counting electron domain number. All right, so these kinds of questions are a little bit easier. I just point to an atom and you tell me what the hybridization is. So really the question is just asking, how many electron domains are around it. That's basically what it asks. What students, we'll ask students these types of questions, which students will think are insanely harder, but It's basically the same question. So it's the same molecule here, the same molecule. But instead of asking you what is the hybridization of each of these atoms, instead I'm asking you what orbitals are involved in forming these bonds. And students think it's like insanely hard, but basically it's the exact same question I asked you before. Because when we form bonds, according to valence bond theory, we're overlapping two orbitals. All right, so that's the idea. We just need to look at what orbitals are the unpaired electrons coming from the adjacent atoms. So when we think about this bond being formed right here, we want to think, okay, where is that electron on hydrogen coming from? Where is the electron from the carbon atom coming from? We already figured out the carbon atom. What was the hybridization of that carbon atom? sp3. So that's one of our orbitals. That's one of them. Where is what orbital is that unpaired electron on hydrogen? It's just an s orbital, so we can just say hydrogen 1s. So hydrogen does not hybridize. It doesn't hybridize. So that's where the unpaired electron is. All right. So see how it's not that hard of a question, but just how it's worded, students, like their brains explode. Okay. All right. So the next one. All right. So the question is, what two orbitals are overlapping to produce that bond? So what we're doing is we're thinking, okay, where's the unpaired electron on that carbon? Where's the unpaired electron on that carbon? We already answered this in the previous question. Basically, I just am asking you, what are the hybridizations of those two carbon atoms? So the bond is being produced by the left carbon's sp3 hybrid orbital, and the adjacent carbon, its unpaired electron is where? In a sp2 hybrid orbital. That's it. That's it. All right, the next one. The carbon, what orbital is that electron in? sp2. And what about oxygen? sp3. Are you following me? We good? So basically this question is just asking what is the hybridization of the two adjacent atoms. Unless it's like oxygen or fluorine or something, then we can use atomic orbitals there, all right? And then the last one here. We have oxygen overlapping with a hydrogen. So the oxygen, we already answered that here. Its unpaired electron is an sp3 orbital. Where's the electron on that hydrogen atom? Just the 1s, yeah, just the 1s, because hydrogen does not hybridize. For fun, if that last atom wasn't hydrogen, let's say it was fluorine, how would that last question change? So we're still, from oxygen, the unpaired electron is still in an sp3 orbital, but now if you think about where is the unpaired orbital or unpaired electron on fluorine, where is it? It's not quite sp3. So fluorine does not need to hybridize. It does not need to hybridize. So it's actually just coming from a 2p orbital. So I'll just go back up here thinking about, where is it? Up here. All right, when we looked at chlorine, these orbitals are in the correct overlap orientation to make these linear bonds that we have. So it's fine when they come from p orbitals. All right. Okay, so there we go. There we go. How do we feel about hybridization and valence bond theory? Do we feel okay? Feel okay? Do we see the purpose of it? It's hard to teach this, I'm telling you. It's really hard, but I've gotten better. I've gotten better. Okay. All right. Okay. So valence bond theory, the great thing about it is it explains multiple bonds too. So for fun, let's, what are the hybridizations of these two carbon atoms? Both of them are sp2 hybridized because both of them have 3 electron domains. All right. The idea here is, okay, they're sp2 hybridized, but there's 3 p orbitals in a p subshell. So the question is, what does that unhybridized p orbital do? And in order to talk about multiple bonds, that's what that unhybridized p orbital does. All right, so what about this molecule, this carbon-carbon triple bond? What's the hybridization of those carbon atoms? It's just sp. How did we get that? Just 2 electron domains, that's it. 2 electron domains for both of them. So the idea here, okay, to make the hybrids, we combined an s and a p orbital, but what did we do with those leftover unhybridized p orbitals? They still have to do something. So that's where valence bond theory can describe multiple bonds as well. So let's look at some examples. So we'll talk about multiple bonds in the idea of valence bond theory. Okay. So I need to clarify a little bit. So when we talked about forming single bonds with valence bond theory, I said, okay, 2 orbitals overlap in space. All right, when we think about like 2 different s orbitals, okay, we have 2 s orbitals, and I said, oh, you bring them close together, they overlap in space, okay, and that overlap is what makes a covalent bond. Specifically, that type of bond we call a sigma interaction. It's a sigma bond, this head-on overlap. All right, it's the strongest type of overlap. It makes the strongest type of bond. So now we have this new interaction to talk about. It's called a pi interaction. All right, so this head-on overlap is sigma. What a pi interaction is, it's overlap, but it's not as direct. I like to call it side-by-side overlap. Pi interactions are made from adjacent p orbitals. So if we think about like 2 different p orbitals, all right, on 2 different atoms, if we bring them close together like this, see how we have a little bit of overlap happening right here, okay? So that overlap is kind of like the overlap with our sigma interaction we were talking about before, but this is much weaker. So this is what we call a pi interaction. It is only made from adjacent p orbitals, all right? But the p orbitals have to be this way, all right? They can't be like this because that's what this interaction is showing. So see how this interaction between p orbitals is a head-on overlap. We see that, the difference? Versus in this picture, our pi bond, or pi interaction, the p orbitals are in this side-by-side overlap, right? So that's the big difference. So what's important about a pi interaction is that when we talk about single bond, double bonds, triple bonds, all right, not all of the interactions are the same. If we think about a single bond, it's 2 electrons, right? 2 electrons are forming that bond, right? It's the 2 electrons in orbitals that are colliding like this in this head-on overlap. In a double bond, how many electrons are in that bond? 4, all right? There's 4 electrons. One of the pairs of electrons are overlapping like this. And, you know, if you were just kind of guessing, you might think, oh, both of the interactions are this head-on overlap. But that's actually not true. The first part of our double bond is a sigma interaction, but the second component is actually a pi interaction. All right, so that's the big idea here. And this actually explains a lot of our bond enthalpies that we've observed, and I'll show you that to you in a little bit. So the second component of a double bond is not another sigma interaction, it's side-by-side pi interaction. And then finally, our triple bond, how many electrons total are there? 6. So those 6 electrons, we have the first component is sigma, the head-on overlap. The second component is a pi interaction, the side-by-side, and then another interaction, the 5th and 6th electron are also in another pi interaction, but it's in a different plane. All right, yes. Because remember, our p orbitals are x, y, z, so it's in a different plane. So we have 2 of these pi interactions. They're just kind of, they're in different planes. All right, so keep that in mind. So I'm going to show you these different orbital interactions because that is what valence bond theory is, right? So let's look at a compound with multiple bonds. This is a little bit harder to explain because we don't technically have a central atom here. So what we want to focus on are the 2 carbon atoms in this carbon-carbon double bond. So each of those carbon atoms are what hybridization? How many electron domains? 3, so sp2. sp2, right? So that means we combine an s orbital, 2 p orbitals, but that means we have that third p orbital is unhybridized, right? It's not part of the hybridization. I'll show you the purpose of that. So that's what we have here. All right, so each carbon is 3 electron domains, trigonal planar. Valence bond theory says sp2. We combine these 3 orbitals, and we get a set of 3 hybrids, our sp2 hybrids, so there's 1, 2, 3 of them, and there's our lonely unhybridized p orbital at the end. So the idea here is that last one is unhybridized. So the important thing to know here is when we put these electrons rearrange our electrons for the carbon atom in our new hybrids. The unhybridized p orbital is a very similar, if not the same energy as the hybrids. So we put all of those electrons in singly. So what I'm trying to say is don't make the mistake of putting that fourth electron spin down like that. You want to put that fourth electron following Hund's rule, because that unhybridized p orbital is the same energy as the hybrids. All right, so you just spread them all out into all four orbitals. So the important thing is here is we have these three hybrids. They're in the trigonal planar shape, and then we have this unhybridized orbital at the end. So we'll see the significance of that down here. All right, so we have these sp2 hybrids. Remember, we have two carbon atoms in this molecule. Each of them are sp2 hybridized. So each of those sp2 hybrids has an electron in it. So that's what this picture is trying to show you. These are all the sigma interactions, right? These are all the sigma interactions involved in this molecule. If we look at the whole molecule, right? Carbon, carbon, all right, and then a bunch of hydrogens like that. All right, let's focus on one carbon. This carbon is bonded to another carbon, right? So that one electron is going to form a sigma interaction with the other carbon atom. What are the other two hybrids interacting with? One's a carbon atom. This central carbon atom is also bonded to what else? The hydrogen. So the other two electrons in hybrid orbitals are involved in the bonds with hydrogen. And so it's basically the same thing with the other carbon atom too. That other carbon atom is bonded to another carbon atom and two other hydrogens. That takes care of all of the sigma interactions, right? All of the sigma interactions of the molecule. And that's what this is trying to show. Each of these big lobes is a hybrid orbital. And so you see here's the overlap being described. But the problem is I didn't do anything with these orbitals yet, right? I didn't do anything with them. This interaction, these two electrons in different adjacent p orbitals, that's the pi interaction for the double bond, all right? So that's the last interaction. These two electrons are involved in the pi interaction that forms the second component of that double bond. Because remember, a double bond has a sigma component. That's what this is right here. That's the sigma component of the double bond. Then the other component is the pi interaction, and that's right here. So the other two electrons that are involved in that double bond, because there's a total of 4, is coming from these pi interaction, the pi interaction between two adjacent p orbitals. And that interaction actually lies above and below the plane of the molecule. So the plane of the molecule has all the sigma bonds. The pi interaction is actually perpendicular to the plane of the molecule. And that just has to do with what leftover p orbitals are there that aren't involved in hybridization, all right? So those are the other two electrons involved in the bond. So just to kind of overview, sigma interactions, pi interactions. Remember, sigma interactions can happen between a lot of different orbitals. They can happen between atomic orbitals, as long as it's a head-on overlap. You can have like two s orbitals, you can have an s and a p orbital, you can have two p orbitals. Those are all sigma interactions because it's the head-on overlap. Or you could have a hybrid orbital and another hybrid orbital or an s orbital, that type of interaction. What's new here are pi bonds or pi interactions, where we have this interaction out of the plane of the molecule, and it's that side-by-side overlap. But the thing with pi interactions is that it's only made from unhybridized p orbitals on a molecule. So yeah, so there we go. All right, so looking at all of this, kind of summarizing again, single bonds only have that head-on sigma overlap interaction. Double bonds, one of them is a sigma interaction. The next component, the other two electrons, have that pi interaction. And then a triple bond is a sigma, a pi, and another pi that's in a different plane from the first one. So the idea here is the beginning of valence bond theory. I mentioned more overlap, stronger bond. So based upon overlap, what do you think is stronger, a head-on overlap or a side-by-side overlap? head-on is much stronger. And so we actually see that in bond enthalpies. So if we look at like a carbon-carbon single bond, it has a bond enthalpy of about 350. So, you know, if you just thought that a double bond is basically twice a single bond, like most people would think that, okay? You would think that the enthalpy of a carbon-carbon triple bond, wouldn't you think it would be double a single bond? But is it? It's not quite double. No, if it was truly double, the enthalpy of a double bond would be 700, right? But we see that the double bond, when it does get stronger, but not exactly double. And that's because the added component here is not another sigma interaction, it's actually a pi interaction. And then the same thing with a double bond to a triple bond, it's another pi interaction, all right? And so we don't see a quite doubling effect here with bonds. It does in fact get stronger, but not like a full doubling effect here. And that has to do with the idea of valence bond theory, where orbital overlap is making your covalent bond, and is the amount of overlap is related to strength there. All right, so we'll look at some more examples here on Wednesday.